Yeah, today I will talk about the fundamental properties relevant to design our ULTERAs. It's the ultra high temperature refractory alloy. It's modeling and the DFT calculations. Here, the modeling include two parts. One is the DFT, the other is the CALPHAD modeling and machine learning. Here is today's contents, the design goal of this project, and the associated fundamental properties. Then I talk about the basic of the modeling and the DFT calculations, including majorly three parts: CALPHAD modeling, machine learning modeling, and the high throughput DFT calculations. And also talk about the fundamental properties relevant to our alloys. The major one is include the diffusion coefficients, elastic properties, surface energy, and the property from the general the stacking fault energy curve, including stress and energy. Finally, the summary of today's talk. And based on last 2 months' work from the students, we know majorly we'll talk about these 4 kind of design criteria. Is the first 3, last one is the strain stress curve. First one, our alloy will with the creep strain is this requirement. We can check Masa's PPT file. We found that the fundamental properties including majorly these 3, the diffusion coefficients, the stable stacking fault energy, and the elastic properties. These properties relevant to the creep. And also in Shang's PPT, we can find the tensor elongation. This one is majorly determined by the fundamental property of surface energy, its unstable stacking fault energy, and the elastic properties. And also in Hui's presentation, we learn that the fracture toughness can be predicted by the fundamental properties of surface energy, unstable stacking fault energy, also the elastic properties. Also, based on Dr. B's work in their group, the strain stress curve can be predicted by final element simulation plus the input with DFT. This model is in this publication, is archive. And also the major input is 2 properties. One is the ideal shear stress and the elastic properties. These are all the target properties. Then we summarize it. We can see the fundamental properties in our work, including the following 5. The first one is not today's major focus. Ours phase stability. This one, based on this property, is it is the free energy to determine the stable phase for each alloy. And we can see from the previous slides, we have 4 major properties. Is the diffusion coefficients, elastic property, surface energy, and the stable, unstable stacking fault energy, also the ideal shear stress. This one can, for each phase, we need these 4 properties. Then we can predict the creep, elongation, fracture toughness, and the strain stress curve. And all these properties will give to West's group for the inverse design. Now, when we predict the fundamental properties, here we majorly use 2 methods. One is the DFT calculations. For the DFT calculations, we will develop and use our new tools. We call the DFT toolkit. Is these tools, and also we can do the modeling. Modeling is 2 kinds of modeling. One is the CALPHAD kind of modeling. The other is the machine learning kind of modeling. When we do the CALPHAD modeling, Usually we use this equation. For example, as a Gibbs energy, we use this sublattice. It's the A, B, and C, D. The capital A, B, C, D are elements. The small a, B is the sublattice, this ratio. We know first we need this 4 end member integers. It's here is phi 0, and also include the interactions. Interactions here we read down is the binary interactions and also the ternary interactions. The first term, if they are for the Gibbs energy, we including the configurational entropy contribution. If they are not the Gibbs energy, this one can be ignored. And then we include the binary interaction is phi L. Sx is the composition for this in this alloy. And also here is the ternary interaction. This one is phi is the interactions. When we want to get this parameters, is the binary parameter and the ternary parameter. We majorly have 2 input. One is the property of the dilute alloy. It means very close to the end member, this point. And also we also need the properties for the concentrate alloy. This one we want to use the SQS. SQS is means the special quasi-random structure. I will give more detail in the following slides. This means the composition in the middle. If we have this end member properties, if the dilute properties is close to end member and in the between, and then we can use this equation to do the CALPHAD modeling. Another type of modeling is we also call the regressions. We can use the machine learning. We have a lot of algorithms, such as the linear regression neural network, and the random forest, and the Gaussian process. Is also we majorly use these 2 models. First is not our focus, but I will talk about our major one. For the free energy, we are using the quasi-harmonic approach based on Dft calculations. Based on Dft calculations, we can predict the 3 properties for each alloy. One is we call the static energy at 0K. It means without any vibrational contributions. They are function of only the volume. We can use the Dft calculations. Here we can use WASP, use our Dft TK to do the predictions. The second term we call the vibrational contribution. It's a function of volume and the temperature. We can use the phono calculation to do the prediction or the domain model. For phono calculations, we can the input is only the phono dots, phono density of states. And the third contribution, the right one, is we call the thermoelectronic contribution. It's a function of also the volume and the temperature. We can use the Dft to predict the electronic dots here. From electronic dots, we can get the this free energy as a function of V and T. The vibration also function of V and T. Its 0K properties is only the contribution of a function of volume. When we added them together, we can get the we call the Helmholtz free energy as a function of V and T. Based on this one, we can predict the phase stability. And the first fundamental properties is the diffusion coefficients. We can claim our group is almost the first group to predict, use the Dft completely, use the Dft to predict the diffusion coefficients. we can predict the self-diffusion coefficient, also the dilute diffusion coefficients. For the alloys, for FCC and the BCC, we can use the fail frequency. Also HCP, we can use the eta frequency. The major one is we use this equation. Here, the F is the factor relative to the structures. A is the lattice parameter. CV is the vacancy concentration. W is the frequency. That is, we can predict use this method. This frequency, we can use the energy to predict. One we call the equilibrium vacancy. This configuration is this energy. The other one, when we go to the in the saddle point, we call the saddle configurations. We base on NEB calculation. We can predict this energy landscape. Then we can get this W value. And also based on this equation, and the second one is the well-known equation, we call the Arrhenius equation. D0 is we call the factors for the diffusion. Q is the vacancy formation. This major one is in the literature we want to determine. This is for the dilute alloy. For concentrate alloy, is more difficult. Usually we didn't do the calculations. We can use the similar as the previous one. We can use the 13 frequency model, or use the MD or MC is the molecular dynamic and the Monte Carlo simulation to do the predictions. And since our project, we want to get the diffusion coefficient very quickly, then we can use the empirical model also. This empirical model is this diffusion coefficient is self-diffusion coefficient. Is first two. Second one, we can link to the dilute diffusion coefficient. Based on this equation, we know if we know three of them, we can predict the fourth one. As we also read down this diffusion coefficient as the equation for prefactor, and the Q is the activation energy. And then for the activation energy, we use this linear combination. For the prefactors, we use this log terms. And here is two examples. It's based on our previous publication. It's a Q value and this prefactor value. It's almost a linear relationship. It means for the self-diffusion and the impurity diffusion, if we know three quantities, then we can predict the fourth one. And also the diffusion coefficient can be predicted from machine learning. Here, the diffusion coefficient also about the dilute, or we call the impurity diffusion coefficient. We have the descriptors, we have the algorithm, then we can predict the diffusion coefficients. Here is example, also the activation energy. And also, they have a lot of resource in the literature. This website is from NIST, is one of our previous postdoc. No, she's faculty in Sweden. They collect all the published self-diffusion and the impurity diffusion data, both the measurements and also the DFT calculations. It means for the self and the impurity diffusion coefficients, we can easily get based on the data in the literature. And then next, we want to get the diffusion coefficient for the concentrated alloy, is our high entropy alloy. And one method we can, based on this three methods, based on different level, we can do the machine learning based MD simulation. It means the force field from machine learning. but this is still time-consuming work. The second one is we can base the CALPHAD modeling to predict the diffusion coefficient for the concentrated alloy. We use two contributions. One is from the thermodynamic. We use the thermodynamic factor and plus the mobility data. This also needs some time. The easy one is we can use the linear combination, such as for one of our high entropy alloy. We can use the linear combination of self-diffusion coefficients of the Q is the activation energy and the prefactors. And we can, based on their composition and do some linear combination, we can easily to get the diffusion coefficient as the first approach. For accurate result, we can use the CALPHAD modeling or machine learning based MD prediction. Now we move to the second property. Second properties is the elastic properties. As currently the elastic properties from Dft calculation is quite a routine work. We have our first publication is 2007. We can predict the elastic properties at 0 Kelvin and also high temperature. At 0 Kelvin and if we at a given volume, we can use the strain stress relationship. Then we can solve this equation to find the CIG values. This equation is based on Hooke's law. In practice, we can give the strains. Based on Dft calculations, we can get the stress. When we have the strain and the stress, we can get the CIG is the elastic constant at a given volume. Now we have the CIG matrix at a given volume, and also based on our previous quasi-harmonic approach, we can predict the volume as a function of temperature. When you cancel this volume, then we can get this elastic properties as a function of T. Is we have published 10 years ago. We still can use it. The prediction is this prediction for single crystal, and also for polycrystal, we can easily get the properties based on the single crystal properties CIG, such as we can get the bulk modular is B, and the shear modular G, Young's modular, and the Poisson's ratio based on these simple equations. And also, because the elastic properties is our major properties for the predictions, then we check what's the source we can find in the literature from DFT and the experimental result. For pure elements, for all the pure elements in BCC, FCC, and HCP structures, we have publications in our group. And also for dilute alloys, we have the nickel-based, magnesium-based, and aluminum-based, and also nickel-3 aluminum-based predictions. And also based on the publications in the literature and also our own observations, usually the elastic properties, they follow the linear combinations, such as the paper in Yale's publication. They use the linear combination, and based on experimental data, they found these trends. And also, we also can find a lot of publications in the literature and also a lot of work. They use machine learning can predict the CIG values. Here, our conclusion is the elastic properties is quite easy to get. And also the third property is surface energy. Surface energy is difficult to predict, but unfortunately, in the material project, they have DFT predictions for surface energy for almost all the pure elements, the stable and the metastable. Here I give two examples as happening. FCC halvening is the metastable case, and the HCP halvening is a stable case. We can find the surface energy, such as surface energy, the lowest one for FCC case usually is 1-1 plane, and also for HCP case is the basal plane is 0-0-0-1 plane. We can find this one. If this is for the alloys, for the simple one, we can use the linear combination based on the alloy composition and the pure element data. We can estimate the surface energy. But for surface energy, when we do the calculation for concentrate alloy, we can use the one structure they call the SQS. This is proposed by Alexander. It means the special random structure. This one, this idea is they use the correlation function is a set of numbers. They call we claim it a set of correlation number is one-to-one corresponding to a given structure. Then we for any structure they have a correlation function. Also for disordered structure, we also can easily calculate it. And also we can compare this correlation function for disordered structure with all. We cannot find all of them. Then we can find the many ordered structure. We can find which one gives the correlation function is very close to the benchmark. Is benchmark. Then we can find a special quasi-random structures. This example is based on our previous work. Is for quaternary alloys, the BCC Jiego. These are SQS structures. For surface energy, also for other properties, if they are for the concentrate alloy, we can use this method. The last kind of properties we call the properties from the generalized staking for the energy curve. This curve can be predicted from DFT. We use the shear deformations. These shear deformations, based on this shear, they can involve one plane, two plane, or many planes. For this two extreme case, we give two names. One is we call that this one is Alice shear. This one is Eiffel shear, and this shear is very close to the real case. Then in our calculations, we can use the Alice shear to do the predictions. Here, this figure is for the FCC structures. The FCC structure during the shear process is the same to the HCP. The HCP is the AB structure. FCC is the ABC structure. During the shear, the HCP also can go to the ABC structures. Then the this 1-1 plane and also the HCP basal plane, they are same plane. Here, next we give one example for FCC nickel. Based on FCC nickel, we on the close packed plane 1-1, and also we do the shear deformation along the 1-1-2 direction is a close packed directions. And also we, as we mentioned, we have one Alice shear and Eiffel shear. And the major one is this Alice shear. One is simple, we call the simple shear and the pure shear. Simple shear is without relaxations of the after shear. The pure shear means after shear deformation, we relax the structures. This one, the pure Alice shear, is very close to the real case. Then we can take a look based on this curve, which properties we can get. The major one is the three properties. One is the staking photon energy, this one. Staking photon, and also the unstable staking photon energy is this energy. And also based on the stress curve, we can the maximum stress here, we can get the ideal shear stress. In our work, all these three properties are relevant to our material design. The major one is the unstable static photo energy and the ideal shear stress. Based on our previous project and also the current one, we have the predictions for pure elements, also the dilute alloys. And here is I mark is the yellow one is for FCC, the green one is for FCC, and the green one is HCP, and also 3 diamond structure. When I have these numbers in, it means we calculate the dilute alloy. If without this number in, it's only for pure FCC. For all this periodic table, the interesting alloys, we have these predictions. It means we have all these properties. These properties as this unstable static photo energy and the ideal shear stress. We have these properties. Based on the easy linear combination, we can merge to these alloys. Here I give two examples. One is for the HCP hafnium. The other one is for BCC, FCC and HCP hafnium. Based on this curve, we can find this ideal shear stress. Based on this curve, we can get the unstable static photo energy. This two structure is for the FCC. The red two is for the HCP. We have all these pure elements, this result. Here, then we take a look, check for the based on the generator static photo energy. We can get the unstable static photo energy and also the ideal shear stress. We almost finished its pure element calculations, and also the for dilute alloy is more than half we finished. We can use our simple first approach, linear combination based on the composition. We can get the properties for the concentrated alloy. Also, we can use the SQS, this structure. We can calculate the properties for concentrated alloy. Also, based on the machine learning, we can get the real, more accurate properties for concentrated alloy. And also, we found we can use the machine learning to predict the properties for more alloys. Here is a summary. Our target is the inverse design of this refractory alloys. It's 4 properties our concern about this creep, the elongation, tensile elongation, fracture toughness, and the strain stress curve. The fundamental properties include diffusion coefficients, stable and unstable static photo energy, elastic properties, surface energy, and the ideal shear stress. We majorly based on first principle calculations, machine learning predictions, CALPHAD modeling, and the final elements modeling. This one is in Alice B's group. Here is the major software we plan to use. The Dft TK is for first principle calculations. This one is machine learning. It's called CALPHAD modeling, and the Abacus is for the final elements simulations. Yes.